Wait! What you're about to see in the next seconds has been hidden for 200 years. And once you understand why, your view of the universe will change forever. One single formula. A forbidden discovery. Two men who knew too much. Cambridge, 1783. Professor John Michell stares at his calculations, his hands trembling, sweat pearls on his forehead. What he just mathematically proved cannot exist. He seals the letter that very night. The Royal Society will bury it in their darkest archives. Too incredible. But across the channel in revolutionary France, a young genius named Pierre-Simon Laplace is about to discover the exact same terrifying truth. Two brilliant minds, two nations. One dark secret so powerful that even Einstein will later desperately try to prove it impossible. 2019, we prove they were both right. And what we find is worse than anything they could have ever imagined. This is their story. The story of two men who discovered something so terrifying that even Einstein fought to disprove it. The most powerful and dangerous objects in the universe. Objects that would become his greatest nightmare. And our reality. The real drama unfolds in what we call the accretion disk, nature's ultimate pressure cooker. At temperatures exceeding 100 million degrees Celsius, atoms don't just break apart. They're torn to shreds in a magnetic maelstrom that would make our sun's worst tantrum look like a gentle breeze. But here's where it gets interesting. Just when you think all that matter is doomed to disappear forever, something remarkable happens. Like a cosmic fountain, some of this superheated material gets launched back into space in massive jets that stretch for thousands of light years. These jets are nature's way of saying not so fast to the black hole's endless appetite. They're also sending us a message about the true nature of these enigmatic objects, one that we're still trying to decode. The closer we look at black holes, the more mysteries we uncover. While our instruments peer ever closer to the event horizon, that point of no return, we're faced with increasingly bizarre phenomena. Time slows down, space bends, magnetic fields twist into impossible shapes. And just when we think we understand what's happening, quantum mechanics throws us another curveball. Astronomers around the world are watching these cosmic behemoths, waiting for the next revelation. Will it confirm our theories, or force us to rewrite our physics textbooks once again? The answer lies somewhere beyond that dark boundary where space and time trade places, where our mathematics breaks down, and where reality itself seems to unravel. But perhaps the greatest mystery isn't what happens inside a black hole. It's how these seemingly destructive objects end up being so crucial to the very existence of galaxies like our own. In a universe full of paradoxes, this might be the greatest one of all. The clock is ticking, and our instruments are getting better every day. We're on the verge of seeing things Einstein himself couldn't have imagined. What will we discover next? Only time, if it even exists where we're looking, will tell. Within the photon sphere, a region roughly 1.5 times the radius of the event horizon, light performs an intricate ballet that challenges our understanding of space-time. Photons can orbit the black hole multiple times before either escaping or plunging past the event horizon, creating a series of nested images called Einstein rings. These ghostly manifestations allow astronomers to observe the same distant object multiple times from different angles, providing crucial data about both the black hole and the space-time fabric itself. The light paths become increasingly complex closer to the event horizon, where extreme gravitational lensing creates multiple images of background stars and even the accretion disk itself. This phenomenon was spectacularly demonstrated in 2019 by the Event Horizon Telescope's groundbreaking image of the supermassive black hole M87, where the asymmetric bright ring revealed the complex interplay between matter, energy, and the extreme curvature of space-time. The event horizon itself represents a unique boundary in physics where quantum mechanics and general relativity must somehow reconcile. Near this boundary, Extreme frame-dragging effects caused by the black hole's rotation can drag space itself along with it, creating regions where matter is forced to orbit in the same direction as the black hole's spin. This effect, known as the lens-Thirring precession, combines with complex magnetic field geometries to possibly power the launching mechanism for those tremendous relativistic jets. The exact nature of the event horizon continues to spark intense theoretical debate, particularly regarding the fate of information that falls into a black hole, the infamous information paradox that has puzzled physicists for decades. Recent observations have revealed even more complexity in black hole systems. The discovery of gravitational waves from merging black holes by LIGO and Virgo has opened an entirely new window into these objects, allowing scientists to probe the dynamics of spacetime itself. These observations have confirmed key predictions of general relativity, while simultaneously raising new questions about the nature of gravity and the structure of spacetime at the quantum level. The detection of quasi-periodic oscillations in X-ray emissions from accreting black holes has provided new insights into the behavior of matter under extreme conditions, while studies of galactic centers have revealed intricate relationships between black hole mass, star formation, and galaxy evolution. The role of black holes in cosmic evolution has proven to be far more profound than initially suspected. Through their intense radiation and powerful jets, supermassive black holes can regulate star formation in their host galaxies through a process called AGN feedback. This feedback mechanism helps explain the observed correlation between black hole mass and galaxy properties, suggesting a deep connection between these cosmic behemoths and the large-scale structure of the universe. Furthermore, the discovery of primordial black hole candidates has raised intriguing possibilities about their role in seeding galaxy formation and potentially contributing to the mysterious dark matter that pervades the cosmos. Breakthrough observations continue to reveal new layers of complexity in black hole systems. Advanced computer simulations incorporating general relativity, magnetohydrodynamics, and radiation transport are beginning to capture the intricate interplay between these various physical processes, providing new insights into jet formation, accretion dynamics, and the behavior of matter under extreme conditions. These simulations, combined with increasingly sophisticated observational techniques like very long baseline interferometry and X-ray polarimetry, are helping to bridge the gap between theoretical predictions and observational evidence, while simultaneously revealing new mysteries that challenge our understanding of the universe at its most fundamental level. Sagittarius A star, anchored 26,000 light-years from Earth in the heart of our Milky Way galaxy, serves as humanity's nearest laboratory for studying the extreme physics of supermassive black holes. While considered relatively modest on a cosmic scale with a mass of 4.3 million suns, this gravitational titan still creates a distortion in space-time powerful enough to profoundly influence the dynamics of the central parsec of our galaxy. The forces at play compress matter into an extraordinarily dense region smaller than our solar system, creating what astronomers call a singularity, a point where the known laws of physics begin to break down. The black hole's profound gravitational influence becomes particularly evident when observing the behavior of nearby stars, which are forced into highly elongated elliptical orbits that would appear bizarre and impossible in more typical gravitational environments. The most thoroughly studied of these stellar dancers is S2, a remarkable blue-white star approximately 15 times more massive than our Sun. During its 16-year orbital period around Sagittarius A star, S2 traces an orbital path that provides astronomers with unprecedented opportunities to test fundamental physics. At its closest approach to the black hole, called periaps, S2 accelerates to an astonishing velocity exceeding 25 million kilometers per hour. A speed so extreme that it could traverse the distance between Earth and the Moon in just 1 minute. During these close encounters, S2 experiences gravitational forces so intense that its light becomes noticeably redshifted, providing what Einstein could only have dreamed of: a natural laboratory for testing the predictions of general relativity under extreme conditions. The monitoring of Sagittarius A has revealed an even more dynamic environment than initially suspected. Using advanced facilities like the Very Large Telescope Interferometer in Chile and the Keck Observatory in Hawaii, astronomers have documented regular flares in both X-ray and infrared wavelengths. These explosive events, typically lasting between 30 and 90 minutes, involve complex magnetic processes that astronomers are only beginning to understand. During particularly intense flares, the brightness of Sagittarius A can increase by factors of 100 or more within minutes, a testament to the violent nature of matter destruction near the event horizon. These flares likely result from magnetic reconnection events, similar to solar flares but far more powerful, occurring in the superheated plasma of the accretion disk that swirls around the black hole at near light speeds. The periodic nature of these flares has led researchers to identify what appears to be a 4.6-hour cycle in the infrared emission, suggesting the presence of hotspots in the accretion disk that orbit the black hole at roughly 30% the speed of light. This observation provides crucial insights into the physics of accretion, the process by which black holes consume nearby matter through a swirling disk of superheated gas and dust that reaches temperatures exceeding 10 million degrees Celsius. However, when compared to other supermassive black holes in the universe, Sagittarius A star appears almost quiescent. The supermassive black hole at the center of the galaxy M87, located 55 million light-years away in the Virgo cluster, represents an entirely different class of cosmic monster. This gravitational giant, officially designated M87 star, contains the mass of approximately 6.5 billion suns, more than 1,500 times more massive than our galactic center's black hole. Its immense mass warps spacetime so severely that it creates a dark silhouette against the glowing background of accreting matter, which was captured in historic detail by the Event Horizon Telescope collaboration in 2019, after combining data from 8 radio telescopes across 4 continents. The most spectacular feature of M87 star is its relativistic jet, a massive beam of particles and energy that extends more than 5,000 light-years from the galaxy's center, a distance greater than the diameter of our entire Milky Way. This jet is powered by magnetic fields of unprecedented intensity, estimated to be thousands of times stronger than any magnetic field ever created on Earth. These fields are capable of accelerating particles to velocities approaching the cosmic speed limit, 99.99% of the speed of light. The energy output of these jets is truly staggering, estimated at around 10 to the power of 44 ergs per second, equivalent to the energy released by several trillion suns. The influence of M87 star's jet extends far beyond its host galaxy. As these high-energy particles interact with the intergalactic medium, they create vast bubbles of hot gas that can span hundreds of thousands of light-years. These bubbles, visible in X-ray observations, prevent the cooling and condensation of gas necessary for new star formation, effectively regulating the growth of galaxies across the entire Virgo cluster. This process, known as AGN feedback, demonstrates how supermassive black holes can influence cosmic structure formation on scales vastly larger than their immediate gravitational influence. Recent observations using the Event Horizon Telescope have revealed that M87 star's jet originates from a region just outside the black hole's event horizon, where frame-dragging effects from the rotating black hole twist magnetic field lines into a tight spiral. This process, known as the Blandford-Znajek mechanism, efficiently extracts rotational energy from the black hole itself, converting it into the kinetic and magnetic energy of the jet. The observation of this process in action provides strong support for Einstein's theory of general relativity and our understanding of how black holes can serve as cosmic particle accelerators. The stark contrast between Sagittarius A star and M87 star demonstrates the incredible diversity of supermassive black holes in our universe, from the relatively quiet specimen in our cosmic backyard to the titans that shape the largest structures we observe. Each provides unique opportunities to study the extreme physics that emerges when matter and energy are pushed to their absolute limits. And together, they help us piece together the complex role these objects play in cosmic evolution. Stephen Hawking's monumental work in the 1970s fundamentally transformed our understanding of black holes, revealing them not as simple cosmic vacuum cleaners, but as complex thermodynamic systems that blur the boundaries between quantum mechanics and gravity. The classical picture of black holes as regions from which nothing could escape was shattered by Hawking's mathematical analysis of quantum fields in curved spacetime, opening up entirely new realms of theoretical physics that continue to challenge our deepest intuitions about the nature of reality. The vacuum near a black hole's event horizon manifests as a roiling quantum foam, where virtual particle-antiparticle pairs continuously pop into existence due to quantum fluctuations permitted by the Heisenberg uncertainty principle. These pairs, which might be electrons and positrons, photons, or even more exotic particles like muons or tauons, typically exist for vanishingly brief periods determined by delta E times. Delta T is approximately equal to h bar, where delta E is the energy of the particle pair and delta T is their lifetime. In normal spacetime, these virtual particles rapidly annihilate each other, maintaining the vacuum's net zero energy. However, the extreme gravitational gradient near the event horizon creates an extraordinary situation. When these particle pairs form near the horizon, they experience dramatically different gravitational forces due to their slight spatial separation. Through quantum tunneling, a process where particles can traverse classically forbidden regions, one member of the pair might escape the black hole's gravitational pull while its partner falls inward. This process effectively promotes the virtual particles to real ones, with the negative energy particle falling into the black hole, reducing its mass, while the positive energy particle escapes as radiation. The mathematics describing this radiation reveals elegant connections between quantum mechanics, gravity, and thermodynamics. The temperature of Hawking radiation is given by T equals h bar times c cubed, divided by 8 pi gmk, where h bar is the reduced Planck constant, c is the speed of light, g is Newton's gravitational constant, m is the black hole's mass, and k is Boltzmann's constant. For a solar mass black hole, approximately 2 times 10 to the power of 30 kilograms, this yields a temperature of about 60 nanokelvins, or 6 times 10 to the power of -8 Kelvin. This incredibly low temperature explains why we cannot directly observe Hawking radiation from astrophysical black holes. It's completely overwhelmed by the cosmic microwave background radiation at 2.7 Kelvin. The evaporation process follows a precise mathematical relationship where the power emitted is inversely proportional to the square of the black hole's mass. P equals h bar c to the 6th, divided by 15,360 pi g squared m squared. This creates a fascinating temporal evolution where smaller black holes radiate more intensely than larger ones. A black hole with the mass of Mount Everest, approximately 10 to the power of 12 kilograms, would glow at room temperature, while one with the mass of a car would shine with the intensity of a small star. The final moments of a black hole's evaporation are particularly dramatic. When the black hole's mass approaches the Planck mass, approximately 2.2 times 10 to the -8 kilograms, quantum gravitational effects become dominant. The temperature soars to the Planck temperature, approximately 10 to the power of 32 Kelvin. And the power output reaches an astonishing 10 to the power of 59 watts, briefly outshining the entire observable universe. This final burst would release particles of all types allowed by quantum numbers and conservation laws, including potentially exotic particles we've never observed in our highest energy particle accelerators. This process creates several profound theoretical challenges. The thermal nature of Hawking radiation appears to destroy information about the quantum state of whatever fell into the black hole, violating the unitarity principle of quantum mechanics. This information paradox has spawned numerous theoretical proposals, including the possibility that subtle quantum correlations between emitted particles encode the information, or that information is stored in hypothetical soft hair on the black hole's horizon. The entropy of a black hole, given by S equals K times A over 4L squared to the power of P, where A is the horizon area and L to the power of P is the Planck length, suggests a deep connection between information, spacetime geometry, and quantum mechanics. This led to the holographic principle, proposed by Gerard 't Hooft and Leonard Susskind, which suggests that the information content of any region of space can be described by a theory that lives only on the boundary of that region. This principle has found its most precise realization in the ADS-CFT correspondence, a concrete example of holography that has become a crucial tool in studying strongly coupled quantum systems. Recent theoretical work has suggested even more exotic possibilities, including the idea that black hole evaporation might create baby universes, or that the interior of a black hole might be connected to its own Hawking radiation through Einstein-Rosen bridges, creating a complex network of entangled quantum states that preserves information while maintaining the semi-classical picture of thermal radiation. These ideas continue to drive research at the frontier of theoretical physics, suggesting that Hawking's initial insights might have only scratched the surface of the deep connection between gravity, quantum mechanics, and the fundamental nature of spacetime itself. The holographic universe. What is it? The holographic principle emerged from one of physics' most perplexing puzzles, a paradox lurking in the mathematics of black holes that threaten to unravel our understanding of the universe's most fundamental laws. At its core was a seemingly irreconcilable conflict between Einstein's general relativity, which suggested information could be permanently lost in a black hole, and quantum mechanics, which insisted that information must always be preserved. This tension came to a head in the early 1970s when Stephen Hawking discovered that black holes slowly evaporate through quantum effects, releasing thermal radiation. This process posed a devastating challenge. If a black hole eventually evaporates completely, what happens to all the information about the objects that fell into it? Quantum mechanics demands that this information must survive, yet calculations suggested it was irretrievably lost, a direct violation of one of physics' most sacred principles. The resolution began to take shape through the work of Leonard Susskind, Gerard 't Hooft, and others who proposed a radical idea. Perhaps all the information about objects falling into a black hole becomes encoded on its event horizon, the boundary beyond which nothing can escape. This encoding would work similarly to a hologram, where three-dimensional information is stored on a two-dimensional surface through intricate interference patterns. The mathematics showed that the amount of information that could be stored this way exactly matched what was needed to preserve all quantum information. This insight grew even more profound when Juan Maldacena discovered the ADS-CFT correspondence in 1997. This mathematical relationship demonstrated that a complete description of gravity in a particular kind of curved spacetime, anti-de Sitter space, was equivalent to a quantum field theory operating on that space's boundary, essentially showing that all the physics within a volume of space could be described by theories living only on its surface. This was like discovering that everything happening in a room could be completely described by examining only the walls. The implications of this correspondence extended far beyond theoretical physics. Condensed matter physicists realized they could use it to study strongly interacting quantum systems that had resisted traditional analytical approaches. Problems in superconductivity that had puzzled scientists for decades suddenly became tractable when viewed through the lens of their gravitational duals. The mathematics of black holes was helping to explain the behavior of electrons in ordinary materials. For instance, in studying strange metals, materials whose electrical resistance scales linearly with temperature in ways that defy conventional theories, physicists found that treating them as holographic projections of higher dimensional gravitational systems led to predictions that matched experimental observations with remarkable accuracy. This success suggested that the holographic principle wasn't just a mathematical curiosity, but a deep truth about nature. The principle has also revolutionized our understanding of quantum entanglement, the spooky action at a distance that Einstein found so troubling. Research has shown that entanglement might be the key to how space itself emerges from more fundamental building blocks. Work by Mark van Ramsdonk and others suggests that the smooth geometry of spacetime might be equivalent to patterns of quantum entanglement in the boundary theory, like threads weaving together the fabric of reality. These insights have practical applications in quantum computing, where understanding how information is encoded holographically could lead to new error correction techniques. They're also influencing approaches to quantum gravity, suggesting ways that space and time might emerge from more fundamental quantum mechanical principles. Recent theoretical work has expanded these ideas even further. Some physicists propose that the holographic principle might help explain cosmic inflation, the brief period of exponential expansion in the early universe. Others are exploring its implications for the cosmological constant problem and the nature of dark energy. The mathematics of holography has even been applied to modeling the spread of contagions and the behavior of quantum chromodynamics, the theory of the strong nuclear force. Perhaps most intriguingly, the holographic principle raises profound questions about the nature of reality itself. If our three-dimensional universe is indeed a projection of processes occurring on a distant two-dimensional surface, what does this mean for our concepts of causality and locality? The principle suggests that space itself might be an emergent phenomenon, not a fundamental feature of reality. This would be like discovering that the solidity of matter, which seems so fundamental to our experience, emerges from the quantum behavior of atoms and electrons. The challenge now lies in testing these ideas experimentally. While direct evidence for the holographic principle remains elusive, scientists are developing increasingly sophisticated ways to probe its predictions. Quantum simulators and ultra-cold atom experiments are being designed to test holographic descriptions of strongly coupled systems. Advanced gravitational wave detectors might one day detect signatures of holographic correlations in spacetime itself. This ongoing research represents one of the most ambitious attempts to unify our understanding of gravity and quantum mechanics. From the mysterious physics of black holes to the practical challenges of designing new materials, the holographic principle continues to provide surprising insights into the deep structure of reality. As we push deeper into this territory, we may find that our universe is even stranger and more interconnected than we ever imagined. The Event Horizon Telescope's breakthrough observations represent a watershed moment in observational astronomy. By synchronizing atomic clocks across 8 observatories spanning the globe, from the South Pole Telescope in Antarctica to the Institut de Radioastronomie Millimétrique in Spain, the EHT achieved an effective aperture nearly the size of Earth itself. This unprecedented interferometric array operates at 230 GHz and 345 GHz frequencies, chosen specifically to penetrate the plasma surrounding supermassive black holes, while maintaining sufficient angular resolution to resolve their event horizon scales. The resulting angular resolution of approximately 20 microarc seconds not only enabled the first direct imaging of a black hole's shadow, but also revealed intricate details about the structure of spacetime in its vicinity. The observed asymmetries in M87 star's accretion flow have proven particularly intriguing. The southern portion of the ring consistently appears 30 to 40% brighter than the northern region, a feature that persists across multiple observational epochs spanning 2017 to 2022. This asymmetry cannot be explained by simple relativistic beaming effects alone, suggesting complex magnetic field configurations and plasma dynamics near the event horizon. The EHT observations revealed that the ring's diameter fluctuates by approximately 10% on timescales of days to weeks, indicating turbulent processes in the accretion flow that theoretical models are still struggling to fully explain. High-precision timing analyses of these variations have revealed multiple characteristic frequencies. The primary oscillation occurs with a period of approximately 45 plus or minus 5 days, consistent with orbital timescales at the innermost stable circular orbit, ISCO, for a black hole of M87 star's mass, 6.5 plus or minus 0.7 billion solar masses. Secondary oscillations with periods of 6 to 8 days have also been detected, possibly reflecting magnetorotational instabilities in the inner accretion disk. These timing signatures provide crucial constraints on accretion models and have led to refined estimates of the black hole's spin parameter, currently believed to be A divided by M approximately equals 0.90 plus minus 0.05. The study of relativistic jets emanating from black holes has revealed unexpected complexity. Recent high-resolution observations of M87's jet show that it maintains a parabolic shape out to approximately 105 Schwarzschild radii, transitioning to a conical geometry beyond this point. The jet's opening angle near its base is significantly wider than predicted by simple magnetohydrodynamic models, measuring 55 plus or minus 7 degrees rather than the expected 20 to 30 degrees. This discrepancy has prompted a fundamental reassessment of jet launching mechanisms, with recent theoretical work suggesting that magnetic field lines threading the ergosphere may play a more crucial role than previously thought. X-ray observations have provided complementary insights into black hole physics. Quasi-periodic oscillations detected in stellar mass black holes show a rich frequency spectrum, with both low frequency, 0.1 to 30 Hz, and high frequency, 100 to 450 Hz, components. The recent detection of phase lags between different energy bands in these QPOs, ranging from microseconds to milliseconds, suggests complex radiative transfer processes in the hot corona surrounding the black hole. These observations have been particularly valuable in constraining models of magnetic reconnection and particle acceleration in strong field gravity regimes. The theoretical landscape has grown increasingly complex as physicists attempt to reconcile quantum mechanics with gravity near black holes. The firewall paradox, formally presented in the AMPS paper, Almhiri-Marolf-Polchinski-Sully, 2012, suggests that the requirement for preserving quantum information might necessitate a violent environment at the event horizon, where the local quantum state would have an energy density of order the Planck scale, approximately 10 to the power of 97 kilograms per cubic meter. Competing theories like fuzzballs propose that quantum effects fundamentally alter the classical black hole structure, replacing the singular core with a complex quantum state that extends to the horizon. These proposals make distinct predictions about gravitational wave echoes and quantum scrambling times that may be testable with future observations. The next generation of black hole observations promises even greater precision. The planned upgrade to the EHT network will include additional telescopes and higher frequency observations at 345 GHz, potentially capable of resolving the photon ring substructure predicted by general relativity. This substructure, consisting of multiple nested rings created by photons orbiting the black hole multiple times before reaching the observer, could provide unprecedented tests of strong field gravity. The spacing and relative brightness of these subrings directly encode information about the black hole's mass, spin, and potentially even quantum corrections to classical general relativity. Numerical simulations have become increasingly sophisticated in modeling black hole environments. Modern GRMHD codes incorporate full 3D radiative transfer, turbulent magnetic fields, and particle acceleration processes. However, even these advanced simulations struggle to reproduce all observed features simultaneously, particularly the detailed structure of relativistic jets and the complex interplay between magnetic fields and plasma in the near-horizon region. The computational challenge is immense, requiring resolution of scales ranging from the horizon, approximately 10 to the power of 1 kilometers for stellar mass black holes, to jet termination regions, approximately 10 to the power of 6 light-years. The reconciliation of quantum mechanics and gravity remains physics' greatest challenge, with black holes serving as nature's most extreme laboratory. As we accumulate more precise observations and develop more refined theoretical models, these cosmic monsters continue to surprise us with their complexity. The ongoing discoveries suggest that understanding black holes may require fundamental revisions to our concepts of space, time, and matter, potentially leading to a revolutionary new framework for physics that transcends both quantum mechanics and general relativity. The winter of 1783 closed in around the stone walls of Christ's College, Cambridge, as John Michell worked late into the night, his large frame bent over a desk worn smooth by decades of scholarly pursuits. At 69 years old, the Yorkshire-born natural philosopher had already made his mark on geology and magnetism. But tonight, his mind wandered through darker territories. The candlelight cast dancing shadows across pages of calculations, the flame occasionally guttering in drafts that snuck through the leaded glass windows of his study. Michel's workspace told the story of an orderly mind grappling with extraordinary ideas. Leather-bound volumes of Newton's Principia sat within arm's reach, their pages dog-eared and annotated with marginal notes in his precise hand. Astronomical tables and star charts covered much of the available surface, while a brass telescope part awaited repair in one corner, a reminder of Michel's practical skills as an instrument maker. The core of his calculation was deceivingly straightforward. Apply Newton's gravitational laws to light itself, treating it as corpuscles of matter as Newton had suggested. As his quill scratched across the parchment, the numbers revealed something that made him pause and lean back in his chair, running a hand through his graying hair. According to his calculations, a star with a radius 500 times that of our Sun, but with the same density, would generate a gravitational pull so intense that light itself would be trapped at its surface, falling back like a stone thrown upward that lacks the velocity to escape Earth's pull. The implications were staggering. Such an object would be, by definition, invisible. A dark star floating through space like a phantom ship on a cosmic ocean. Michel meticulously worked through the observational consequences. While these objects couldn't be seen directly, their gravitational influence on nearby visible stars might betray their presence. He even suggested a method for detecting them, proposing that astronomers might find dark stars by looking for binary systems where only one star was visible. Yet the motion indicated the presence of a massive companion. In his paper to the Royal Society, published in the Philosophical Transactions, Michel laid out his reasoning with characteristic thoroughness. The members who received it, including the astronomer William Herschel and the polymath Henry Cavendish, were among the finest scientific minds in England. Yet even they struggled to fully grasp the revolutionary nature of what Michel proposed. The paper was received politely, discussed briefly, and then largely forgotten. Across the Channel, in a France teetering on the edge of revolution, Pierre-Simon Laplace's life followed a very different trajectory. Born into a humble family in Normandy, by 1796 he had established himself as one of Europe's premier mathematicians. The political upheaval that would soon convulse France hadn't yet reached its peak when Laplace settled into his own calculations about gravity's effect on light. Laplace's study in Paris was a contrast to Michel's Cambridge quarters. French scientific culture emphasized mathematical elegance over English empiricism, and Laplace's pages of calculations reflected this aesthetic, filled with elaborate differential equations and carefully derived formulas. He approached the problem through the mathematical framework he had developed for studying gravitational effects in the solar system, a framework so comprehensive that Napoleon once remarked that Laplace had left no work for future astronomers. Working independently, unaware of Michel's earlier discovery, Laplace arrived at the same unsettling conclusion. His core obscures, dark bodies, were described with even greater mathematical precision in his Exposition du Système du Monde. Laplace went further than Michel in some ways, calculating the exact escape velocity needed for light to break free from such an object's surface. His work was more sophisticated mathematically, but the core insight was identical. Gravity could, in theory, trap light itself. The timing of these discoveries proved particularly unfortunate. The scientific world was in the midst of a fundamental shift in understanding the nature of light. The corpuscular theory that both men had used in their calculations was gradually being replaced by the wave theory of light championed by Thomas Young and Augustin-Jean Fresnel. This paradigm shift seemed to invalidate the very premise of their work. After all, how could gravity trap a wave? The papers of both men slipped into obscurity, footnotes in the history of astronomy. Yet their insights, arrived at through pure mathematical reasoning and the careful application of known physical laws, had brushed against a truth so profound that it would take another century and Einstein's complete reimagining of gravity through general relativity to fully appreciate what they had found. Their dark stars would eventually be reborn as black holes, objects so extreme that they rip holes in the fabric of space-time itself. Modern scientists, using radio telescopes and gravitational wave detectors, have confirmed that these cosmic monsters are real, lurking in the hearts of galaxies and roaming the cosmic depths. The Event Horizon Telescope's image of the supermassive black hole at the center of M87 stands as a testament to the power of mathematical prediction, a visual confirmation of what Michel and Laplace had glimpsed through their calculations 2 centuries earlier. The story of these two men, one an English polymath who worked in relative isolation, the other a French mathematical genius at the heart of European science, represents one of the most remarkable examples of parallel discovery in the history of physics. Through different paths, in different countries, surrounded by different intellectual traditions, both men pierced the veil of conventional wisdom to glimpse one of the universe's most profound secrets. Their work reminds us that sometimes the most revolutionary discoveries come not from new observations or experimental data, but from following mathematical logic to its ultimate mind-bending conclusions. Today, as astronomers catalog thousands of black holes and astrophysicists use them to test the limits of our physical theories, the candlelit studies where Michel and Laplace worked have themselves become like dark stars, places where light from the past struggles to reach us, but whose gravitational influence on the development of physics can still be felt, pulling us toward a deeper understanding of the cosmos and our place within it. On a crisp, burn morning in 1905, 26-year-old Albert Einstein walked from his modest third-floor apartment at 49 Kramgasse to his post at the Swiss Federal Patent Office. The position, which paid 3,500 Swiss francs annually, had been a lifeline after rejections from every academic institution he'd approached. At his wooden desk in room 86, surrounded by sketches of electrical mechanisms and clockwork synchronization devices, the young technical expert third class evaluated inventors' claims with remarkable efficiency. The skills he developed scrutinizing patents, analyzing physical problems, detecting hidden assumptions, thinking through implications, would prove invaluable for the revolutionary theories forming in his mind. Between reviewing applications, Einstein conducted elaborate thought experiments that would transform physics. He imagined chasing light beams through space at 186,282 miles per second, pictured identical clocks placed at different gravitational potentials, and contemplated the nature of acceleration while visualizing elevators in free fall. These thought experiments, combined with intensive mathematical work often done late at night after his wife Mileva and young son Hans Albert had gone to bed, led him through an intellectual odyssey spanning a decade. The journey culminated on November 25, 1915, in the August Hall of the Prussian Academy of Sciences. There, Einstein presented his completed general theory of relativity, 10 elegant field equations that revealed gravity as the curvature of four-dimensional spacetime. The mathematics surpassed even the prophetic insights of John Michel, who in 1783 had calculated that a star 500 times the size of the Sun would have an escape velocity exceeding light speed, and Pierre-Simon Laplace, who in 1796 had described dark stars in his Exposition du Système du Monde. Einstein's equations showed that reality was far stranger than either predecessor had imagined. They predicted regions where space-time curvature became so extreme that light paths bent back on themselves, forming what we now call the event horizon. Yet Einstein himself resisted these implications. In a 1939 paper in Annals of Mathematics titled "On a Stationary System with Spherical Symmetry Consisting of Many Gravitating Masses," he attempted to prove such objects couldn't form in nature, arguing that particles circling a dense mass would never actually collapse into a singularity. The story took an unexpected turn in 1967 at a conference on gravitational collapse at NASA's Goddard Institute for Space Studies in New York. John Wheeler, the Princeton physicist who had helped develop the hydrogen bomb and pioneered the study of gravitational collapse, grew frustrated with repeatedly saying, "gravitationally completely collapsed object," during his presentation. Drawing inspiration from an audience suggestion at a talk he'd given earlier that year, Wheeler used the term black hole instead. The phrase perfectly captured both the object's darkness and its ability to trap anything that ventured too close. However, this evocative name contributed to a fundamental misunderstanding that persists today. Popular media began depicting black holes as cosmic vacuum cleaners, roaming space and consuming everything in their path. Films and television shows portrayed them as whirlpools in space, inexorably pulling in nearby matter. The scientific reality, described by Einstein's equations, is more subtle. A black hole with the sun's mass exerts exactly the same gravitational force on Earth as our sun does. Only when approaching within about 3 kilometers of a solar mass black hole's event horizon do the exotic effects of extreme space-time curvature become apparent. The actual physics of black holes involves concepts that challenge human intuition. Gravitational time dilation causing clocks near the event horizon to appear to tick more slowly from an outside perspective. Frame dragging that pulls space-time itself into a swirling motion around rotating black holes, and Hawking radiation suggesting that black holes slowly evaporate over immense timescales. These phenomena, mathematically predicted but pushing the boundaries of what we can observe, remind us that the universe is not obligated to conform to our everyday experiences. Einstein's reluctance to accept the full implications of his own theory mirrors our broader struggle to comprehend these cosmic extremes where the familiar rules of reality break down. In the early 1930s, Swiss astronomer Fritz Zwicky made an observation that would puzzle physicists for nearly a century. While studying the Coma cluster, a massive collection of galaxies roughly 321 million light-years from Earth, he noticed something peculiar. The galaxies were moving far too quickly. Based on the visible matter present in the cluster, the gravitational forces should have been insufficient to hold these galaxies together at such velocities. They should have been flying apart, yet they remained bound in their cosmic dance. Zwicky proposed that some invisible form of matter, which he termed dunkle Materie, dark matter, must be providing the additional gravitational force needed to explain his observations. This initial discovery was largely ignored by the astronomical community until the 1970s, when Vera Rubin and Kent Ford's groundbreaking work on galactic rotation curves brought the dark matter problem back into focus. Their careful observations of the Andromeda Galaxy revealed that stars at the galaxy's outer edges were orbiting at roughly the same speed as those closer to the center, a phenomenon that violated the expected Keplerian motion. According to our understanding of gravity, stars at greater distances should orbit more slowly, just as the outer planets in our solar system move more slowly than the inner ones. This flat rotation curve phenomenon suggested that galaxies must be embedded in massive halos of invisible matter extending far beyond their visible boundaries. Modern astrophysical evidence for dark matter has become overwhelming. Gravitational lensing, where massive objects bend light from distant sources, reveals the presence of invisible mass distributions throughout the cosmos. The Bullet Cluster, a collision between two galaxy clusters 3.7 billion light-years away, provides particularly compelling evidence. Observations show that the bulk of the cluster's mass passed through each other without interacting, while the visible gas clouds collided and slowed down. Exactly what we would expect if most of the mass existed in a form that rarely interacts except through gravity. The cosmic microwave background radiation, our earliest window into the universe's history, tells us that dark matter must have played a crucial role in cosmic structure formation. Small density fluctuations in the early universe could only have grown into the galaxies and clusters we see today if dark matter was present to provide gravitational scaffolding. Current measurements suggest that dark matter makes up approximately 85% of all matter in the universe and about 27% of its total energy content. Scientists have proposed numerous candidates for dark matter particles. Weakly interacting massive particles, WIMPs, were long considered the frontrunners, with masses typically between 1 GeV and 1 TeV. These hypothetical particles would interact through gravity and the weak nuclear force, but remain invisible to electromagnetic radiation. Axions, extremely light particles originally proposed to solve problems in quantum chromodynamics, represent another promising candidate. More exotic possibilities include sterile neutrinos, which would interact even more rarely than regular neutrinos, and primordial black holes formed in the earliest moments of the universe. Detection efforts have grown increasingly sophisticated. Deep underground laboratories, shielded from cosmic rays and other background radiation, house ultra-sensitive detectors filled with materials like liquid xenon or crystalline sodium iodide. The Large Underground Xenon, LUX experiment, located nearly a mile beneath South Dakota's Black Hills, searched for the tiny flashes of light that would indicate a dark matter particle colliding with a xenon nucleus. Its successor, Lux Zeppelin LZ, contains 7 tons of liquid xenon and can detect interactions down to incredibly low energies. Complementary approaches include indirect detection experiments searching for the products of dark matter annihilation in space. The Alpha Magnetic Spectrometer aboard the International Space Station hunts for unexpected sources of antimatter that could signal dark matter interactions. Meanwhile, particle colliders like the Large Hadron Collider attempt to create dark matter particles directly through high-energy collisions, looking for their signature in missing energy and momentum. Despite these extensive efforts, dark matter has proven remarkably elusive. Each new null result helps constrain theoretical models and rule out certain possibilities. But the fundamental nature of this mysterious substance remains unknown. Some physicists have begun to question whether our understanding of gravity itself might need revision, leading to alternative theories like modified Newtonian dynamics, MOND. However, these alternative theories struggle to explain the full range of observations as elegantly as dark matter. The dark matter puzzle represents one of the most profound mysteries in modern physics. Its resolution promises to revolutionize our understanding of the universe's composition and evolution, potentially revealing new fundamental particles or forces beyond the standard model. As detection technology continues to advance and new theoretical approaches emerge, physicists remain optimistic that the nature of dark matter will eventually be unveiled, opening new chapters in our understanding of the cosmos. The astronomical community has witnessed a paradigm shift in our understanding of cosmic evolution with the definitive detection of intermediate mass black holes, IMBHs. These long theorized objects, which bridge the gap between stellar mass black holes, typically 3 to 100 solar masses, and supermassive black holes, millions to billions of solar masses, are revolutionizing our comprehension of universal structure formation. The discovery has been achieved through a sophisticated combination of multi-messenger astronomy, including gravitational wave interferometry, X-ray spectroscopy, and radio observations of accretion signatures. HLX-1, Hyperluminous X-ray Source 1, located in the outskirts of the lenticular galaxy ESO 243-49 at coordinates right ascension 1 hour, 10 minutes, 28.3 seconds. Declination negative 46 degrees, 4 minutes, 22 seconds, has emerged as the prototype for this class of objects. Its X-ray luminosity peaks at approximately 1,042 ergs per second during outburst phases, exceeding the Eddington limit for stellar mass black holes by several orders of magnitude. The system's periodic variability, precisely measured at 370 plus or minus 3 days, corresponds to the orbital period of a donor star being stripped of its outer layers. High-resolution spectroscopic analysis reveals emission lines broadened by velocities exceeding 500 kilometers per second, consistent with material orbiting a compact object of 20,000 plus or minus 5,000 solar masses. The existence of IMBHs provides a crucial solution to what cosmologists term the quasar seed problem. Observations of quasars at redshift Z7, corresponding to less than 800 million years after the Big Bang, reveal supermassive black holes exceeding 109 solar masses. Traditional Eddington limited accretion models, which restrict mass growth to doubling approximately every 45 million years, cannot explain this rapid evolution. IMBHs offer a heavy seed scenario. Initial black holes of 103-105 solar masses, formed through direct collapse of massive gas clouds or dense stellar clusters, could reach supermassive scales within the available cosmic time through a combination of gas accretion and hierarchical mergers. The physics governing the environment near black hole event horizons represents a unique laboratory for testing fundamental theories. At these scales, where the spacetime curvature approaches the Planck length, approximately 10 to 35 meters, quantum gravitational effects become non-negligible. The relativistic jets observed from active black holes, exemplified by M87's central engine, achieve bulk Lorentz factors of gamma greater than 10, corresponding to velocities greater than 0.995 c. These jets, confined by helical magnetic fields reaching strengths of 103 to 104 Gauss, can extend to distances of 5,000 light-years, while maintaining remarkable collimation, with opening angles of just a few degrees. The material within these jets undergoes extreme acceleration through magnetohydrodynamic processes, reaching kinetic energies sufficient for spallation reactions that produce significant quantities of lithium, beryllium, and boron. The jets deposit kinetic energy into their surroundings at rates exceeding 1,045 ergs per second, sufficient to regulate star formation through feedback mechanisms. High-resolution radio observations have revealed that these jets create vast cavities in the surrounding intergalactic medium, visible as bubbles in X-ray images of galaxy clusters. The formation mechanisms for IMBHs have been illuminated by recent advances in computational astrophysics. In globular clusters with central densities exceeding 106 solar masses per cubic parsec, mass segregation drives the most massive stars to the core on timescales of just a few million years. N-body simulations demonstrate that in these environments, the probability of stellar collisions increases exponentially with density. The process begins with the merger of massive main sequence stars, greater than 40 solar masses, through direct collisions. The resulting objects, with masses potentially exceeding 500 solar masses, evolve rapidly and undergo pair instability supernovae or direct collapse to form IMBHs. These newly formed IMBHs continue their growth through multiple channels. Tidal disruption events, where stars are torn apart by tidal forces, occur at rates of approximately 10 to 4 per year per IMBH. The resulting accretion events produce characteristic X-ray and gamma-ray signatures with blackbody temperatures of 104 to 105 Kelvin and peak luminosities, approaching 1,044 erg per second. Gas accretion proceeds through the formation of miniature accretion disks, which have been resolved by radio interferometry showing Keplerian rotation profiles extending to within 100 Schwarzschild radii of the black hole. The merger rate of IMBHs with other compact objects is predicted to be detectable by the planned LISA Gravitational Wave Observatory, which will be sensitive to mergers in the mass range 102 to 107 solar masses out to redshifts of Z greater than 20. These events will produce gravitational waves with characteristic frequencies of 10 to the power of -3 to 10 to the power of -1 Hz, precisely in LISA's peak sensitivity band. The detection of these mergers will provide direct evidence for hierarchical black hole growth in the early universe and constrain theories of gravity in the strong field regime. Advanced numerical relativity simulations suggest that IMBH mergers might exhibit unique gravitational wave signatures due to their intermediate mass ratios. These events could produce higher harmonic modes in the gravitational wave signal, allowing tests of general relativity with unprecedented precision. Additionally, if IMBHs retain significant spins from their formation process, their mergers could provide insights into the poorly understood physics of spin-orbit coupling in strong gravitational fields. The modern era of black hole astronomy has been revolutionized by gravitational wave observatories, with LIGO and Virgo leading a new age of multi-messenger astronomy. These extraordinary instruments can detect distortions in spacetime smaller than 1/1000th the width of a proton, capturing the gravitational echoes of cosmic collisions that occurred billions of years ago. The first detection, GW150914, not only confirmed Einstein's century-old predictions, but opened a new window into the universe, allowing us to observe black hole mergers with unprecedented precision. Since that groundbreaking discovery, these observatories have documented over 90 confirmed gravitational wave events, with dozens involving black hole mergers of varying masses and complexities. The data from these observations has profoundly challenged our understanding of black hole formation and evolution. The detection of GW190521 in particular sparked intense debate within the astronomical community, as it revealed a merger producing a black hole of 142 solar masses, squarely within the theoretically forbidden pair instability mass gap, where conventional stellar evolution models predict black holes shouldn't exist. This unexpected finding has forced astrophysicists to reconsider fundamental assumptions about stellar collapse mechanisms and the role of hierarchical mergers in black hole growth. Subsequent observations have revealed an entire population of black holes that seem to defy traditional formation theories, suggesting the existence of multiple, potentially exotic formation channels. The Event Horizon Telescope collaboration marked another milestone by capturing the first ever image of a black hole's shadow in M87, followed by imaging Sagittarius A at the center of our own galaxy. These images, achieved through a planet-wide network of radio telescopes performing very long baseline interferometry, provided direct visual evidence of the photon ring and accretion structure predicted by Einstein's equations. The asymmetric brightness distribution in these images has allowed scientists to measure black hole spin and test general relativity in the strong field regime with unprecedented precision. Future observations aim to capture time-resolved images of the dynamic behavior of matter near the event horizon, potentially revealing the nature of magnetic field structures and relativistic jets. The theoretical landscape has evolved in parallel with these observational advances. The black hole information paradox, first identified by Stephen Hawking, has spawned numerous proposed resolutions, including the controversial firewall hypothesis and various holographic principles. Recent work by Juan Maldacena, Leonard Susskind, and others has suggested deep connections between quantum entanglement and spacetime geometry through the ER-EPR conjecture, proposing that entangled particles might be connected through microscopic wormholes. This has led to new theoretical frameworks exploring how quantum information might be preserved in black hole evaporation, with some suggesting that information could be encoded in subtle correlations in Hawking radiation, or stored in complex quantum structures at the event horizon. The possibility of using black holes as probes of quantum gravity has gained renewed attention with advances in string theory and loop quantum gravity. These approaches suggest different microscopic descriptions of black hole entropy, with string theory providing a precise counting of microstates for certain supersymmetric black holes through the work of Strominger and Vafa. Loop quantum gravity, meanwhile, offers a different perspective, suggesting that the quantum geometry of spacetime itself might resolve the singularity at the center of black holes. The next frontier in black hole research involves multiple ambitious projects. The space-based LISA gravitational wave detector, scheduled for launch in the 2030s, will be able to detect mergers of supermassive black holes across cosmic history, potentially revealing how these giants grew in the early universe. The next generation of ground-based detectors, including Einstein Telescope and Cosmic Explorer, promise to detect thousands of black hole mergers per year, allowing statistical studies of black hole populations and precise tests of general relativity. Quantum simulation experiments using advanced materials and ultra-cold atoms are beginning to provide laboratory analogs of black hole physics, allowing controlled studies of phenomena like Hawking radiation and superradiance. These tabletop experiments, combined with quantum computing simulations, may offer new insights into quantum effects near black holes that are impossible to observe directly. The role of black holes in cosmology has also gained prominence with suggestions that primordial black holes, formed in the extreme conditions of the early universe, might constitute some or all of the mysterious dark matter. This hypothesis has sparked new observational campaigns looking for microlensing events and other signatures of small black holes in our cosmic neighborhood. The quest to understand black holes continues to drive innovation across physics, from developing new mathematical tools in quantum field theory to pushing the boundaries of astronomical instrumentation. As we peer deeper into these cosmic mysteries, each discovery seems to reveal new layers of complexity in the fundamental nature of space, time, and gravity. The next decade promises even more revelations as new instruments come online and theoretical frameworks mature, potentially leading to a unified understanding of quantum mechanics and gravity through the lens of these most extreme objects in the universe. The story of humanity's understanding of black holes represents one of the most profound intellectual journeys in the history of science, weaving together threads of pure mathematical insight, technological innovation, and observational breakthroughs spanning more than a century. The tale begins in the muddy trenches of World War I, where Karl Schwarzschild, serving as an artillery officer in the German army on the Russian front, made his groundbreaking discovery. Despite suffering from pemphigus, a devastating autoimmune disease that caused painful blistering of his skin, Schwarzschild worked tirelessly in his spare moments between calculating artillery trajectories. Using only pencil and paper, he derived the first exact solution to Einstein's field equations of general relativity, published just months earlier in 1915. Schwarzschild's solution revealed something extraordinary. If matter were compressed into a small enough space, its gravitational field would become so intense that nothing, not even light, could escape. The boundary of this region of no return would occur at what we now call the Schwarzschild radius, equal to 2 gm over c squared, where g is Newton's gravitational constant, m is the mass of the object, and c is the speed of light. For a mass like our Sun, this radius would be just 3 kilometers. Schwarzschild completed this work while experiencing increasing health complications from his disease, sending his final papers to Einstein in December 1915. He died just months later in May 1916, never knowing the full impact his wartime calculations would have on our understanding of the universe. For decades after Schwarzschild's discovery, these objects remained mathematical curiosities that many physicists regarded with deep skepticism. Einstein himself published a paper in Annals of Mathematics in 1939, arguing that such objects couldn't actually form in nature, believing that some physical mechanism would prevent matter from becoming so compressed. The term black hole wasn't coined until 1967, when physicist John Wheeler used it during a lecture at the NASA Goddard Institute of Space Studies. The name stuck, replacing the more cumbersome, gravitationally completely collapsed star. The theoretical understanding of black holes advanced significantly in the 1960s and 1970s. Roger Penrose proved in 1965 that black holes were an inevitable consequence of Einstein's theory, showing that once a certain amount of matter is compressed beyond a certain point, gravitational collapse becomes unavoidable. Stephen Hawking later demonstrated that black holes aren't entirely black. They emit a faint radiation now known as Hawking radiation, with a temperature inversely proportional to their mass. For a black hole, the mass of our Sun, this temperature would be a mere 60 nanokelvin, far too faint to detect with current technology. The modern era of black hole research began with a chirp. At 5:51 a.m. Eastern Time on September 14, 2015, both detectors of the Laser Interferometer Gravitational Wave Observatory, LIGO, recorded a signal that would transform astronomy. The detection, designated GW150914, captured the final 0.2 seconds of a cosmic collision that had taken place 1.3 billion light-years away. LIGO achieved this through an extraordinary feat of engineering, detecting changes in distance smaller than 1/10,000th the width of a proton using laser beams bouncing between mirrors suspended in perfect vacuum. The signal revealed two massive black holes, one 29 times the mass of our Sun, and the other 36 solar masses, spiraling together at half the speed of light in their final orbits. The merger produced a single black hole of 62 solar masses, with the missing 3 solar masses converted entirely to gravitational wave energy in a fraction of a second. The peak power output of this event reached 3.6 times 10 to the power of 56 ergs per second, briefly exceeding the combined electromagnetic power output of all stars in the observable universe by a factor of more than 10. Following this initial detection, LIGO and its European counterpart Virgo have observed dozens more black hole mergers, building up a census of these objects across cosmic time. These observations revealed a surprising population of heavyweight black holes with masses above 50 solar masses, challenging our understanding of stellar evolution and suggesting either previously unknown formation channels or multiple generations of mergers. The Event Horizon Telescope, EHT collaboration, achieved another milestone in April 2019 by capturing the first-ever image of a black hole's immediate environment. This technical tour de force required synchronizing 8 radio observatories across 4 continents with atomic clock precision better than a picosecond. The observatories included the Atacama Large Millimeter Array, ALMA, in Chile's high desert, the South Pole Telescope in Antarctica, the James Clerk Maxwell Telescope atop Mauna Kea in Hawaii, and the Institut de Radioastronomie Millimétrique, IRAM, 30-meter telescope in the Spanish Sierra Nevada. The target was the supermassive black hole at the heart of the galaxy M87, a cosmic monster 6.5 billion times more massive than our Sun, located 55 million light-years away in the Virgo cluster. The resulting image revealed a 40 billion kilometer wide ring of emission around a central shadow. The ring's asymmetric brightness, with a distinct bright crescent on one side, is caused by relativistic beaming. Matter orbiting the black hole at nearly light speed appears brighter when moving toward Earth and dimmer when moving away. The size of the dark central region, approximately 38 billion kilometers across, matched theoretical predictions based on Einstein's equations to within 10%, providing one of the most stringent tests yet of general relativity in the strong field regime. Subsequent EHT observations have revealed the magnetic field structure around M87's black hole through polarimetric imaging. The data showed highly ordered magnetic fields strong enough to resist the intense pull of the black hole's gravity, with field strengths reaching hundreds of Gauss. These strong magnetic fields help explain how black holes launch powerful relativistic jets that can extend for tens of thousands of light years. The jets from M87's black hole carry enough energy, approximately 10 to the power of 44 ergs per second, to influence the evolution of the entire Virgo galaxy cluster, heating the intergalactic medium and preventing the formation of new stars. The next generation of EHT observations promises even more exciting discoveries. Plans are underway to add space-based telescopes to the array, which would be free from atmospheric interference and provide baselines longer than Earth's diameter. This could potentially allow direct imaging of the photon ring, a series of nested rings caused by light rays that orbit the black hole multiple times before reaching Earth. The innermost of these rings would provide the most precise test yet of Einstein's theory in the extreme gravity regime. The collaboration is also working to produce detailed images of Sagittarius A star, the 4.3 million solar mass black hole at the center of our own Milky Way galaxy. Despite being much closer than M87's black hole, Sagittarius A presents unique challenges because it evolves much more quickly due to its smaller size. Matter orbiting M87's black hole takes days or weeks to complete an orbit, while material around Sagittarius A core changes position in minutes. This requires new imaging techniques that can account for this rapid variability. From Schwarzschild's wartime calculations to today's global network of telescopes, our understanding of black holes reflects humanity's remarkable journey to comprehend the most extreme objects in our universe. Each new observation continues to test and validate Einstein's century-old theories while revealing new mysteries. Questions remain about the precise nature of the event horizon, the fate of information that falls into a black hole, and the role these objects played in shaping the early universe. As our observational capabilities continue to advance, black holes promise to remain at the frontier of physical science, challenging our understanding of space, time, and the fundamental nature of reality itself. Black holes lie at the intersection of quantum mechanics and gravity, challenging our deepest physical theories and driving major advances in theoretical physics. The tension between quantum mechanics and general relativity becomes particularly acute in these extreme objects, where classical spacetime geometry meets quantum effects. Stephen Hawking's transformative 1974 paper, Black Hole Explosions, demonstrated through detailed quantum field theory calculations that quantum effects near black hole horizons lead to particle creation and radiation emission. This process occurs because quantum fluctuations in the vacuum near the horizon create pairs of particles and antiparticles. Through a subtle interplay of quantum tunneling and horizon geometry, one particle can escape to infinity while its partner falls into the black hole, carrying negative energy and gradually reducing the hole's mass. The thermal nature of Hawking radiation raised profound questions about quantum mechanics' fundamental principle of unitary evolution. According to quantum theory, the evolution of any closed system must be described by unitary transformations that preserve quantum information. However, Hawking's calculations suggested that when a black hole completely evaporates, it leaves behind only thermal radiation, apparently erasing all information about the initial quantum state of whatever fell in. This apparent violation of quantum mechanics' basic principles sparked intense theoretical debate and research. Don Page's detailed analysis in the 1970s showed that if quantum mechanics is preserved, subtle correlations in the Hawking radiation must encode all information about the hole's contents. Though accessing this information would require gathering and processing all radiation particles emitted over the black hole's entire lifetime. The information paradox took an even more dramatic turn in 2012, When Joseph Polchinski, Ahmed Almheri, Donald Marolf, and James Sully published their firewall argument. Through careful analysis of quantum information theory requirements, they showed that preserving information in Hawking radiation appears incompatible with the principle of equivalence from general relativity. The equivalence principle requires that an observer falling through the event horizon experiences nothing unusual in their local reference frame. However, the firewall argument suggested that maintaining quantum mechanical unitarity would require intense radiation at the horizon that would incinerate any infalling observer. This stark choice between violating either quantum mechanics or general relativity's equivalence principle represented a new level of tension between our fundamental theories. The search for resolutions has led to profound insights about the nature of spacetime and quantum entanglement. Leonard Susskind and Juan Maldacena's ER-EPR conjecture, proposed in 2013, suggested a deep connection between quantum entanglement, Einstein-Podolsky-Rosen correlations, and spacetime geometry, Einstein-Rosen bridges or wormholes. Their work built on earlier insights from string theory and holographic principles, particularly the ADS-CFT correspondence discovered by Maldacena in 1997. This framework suggests that quantum entanglement between Hawking radiation and the black hole interior creates geometric connections through spacetime that could allow information to escape while preserving both quantum mechanics and smooth horizon geometry. Recent work by multiple research groups has expanded on these ideas, exploring how quantum entanglement might serve as the fundamental building blocks from which classical spacetime emerges. The relationship between supermassive black holes and their host galaxies reveals equally profound mysteries on cosmic scales. Detailed observations of thousands of galaxies, using both ground-based telescopes and space observatories like Hubble, have uncovered remarkably tight correlations between central black hole masses and host galaxy properties. The M-sigma relation, first reported by Carl Gebhardt and colleagues in 2000, shows that a galaxy's central black hole mass, M, correlates with the velocity dispersion, sigma, of stars in its central bulge following the precise power law M is proportional to sigma to the fourth. This relationship holds across more than 4 orders of magnitude in black hole mass, from relatively small galaxies hosting million solar mass black holes to giant elliptical galaxies harboring behemoths of billions of solar masses. The scatter around this relation is surprisingly small, typically less than 0.3 dex, suggesting a fundamental physical mechanism coupling black hole growth to galaxy evolution. Modern computational astrophysics has revealed how this coupling likely operates through complex feedback processes associated with active galactic nucleus, AGN activity. When gas falls toward a supermassive black hole, conservation of angular momentum causes it to form a rapidly rotating accretion disk. Magnetic fields and turbulence in the disk transport angular momentum outward, allowing matter to spiral inward while heating the gas to temperatures exceeding 107 Kelvin. At these extreme temperatures, general relativistic effects become crucial. The innermost stable circular orbit around the black hole allows gravitational potential energy to be converted to radiation with unprecedented efficiency, up to 40% of the rest mass energy for maximally spinning black holes. This energy emerges as both electromagnetic radiation across the spectrum and relativistic jets of particles accelerated by magnetic fields to velocities approaching the speed of light. Advanced numerical simulations incorporating detailed physics of radiative transfer, magnetohydrodynamics, and relativistic effects have shown how this tremendous energy output creates a self-regulating system. As gas falls onto the black hole and fuels AGN activity, the resulting energy heats surrounding gas throughout the host galaxy, preventing it from cooling and forming new stars. This creates a feedback loop. Black hole growth leads to increased energy output, which eventually halts further growth by preventing additional gas from falling in. These simulations demonstrate how this mechanism naturally explains both the observed MS relation and the apparent upper limit on galaxy masses in our universe, typically around 10-12 solar masses. Recent work has extended these models to cosmic scales, showing how AGN feedback shapes the evolution of galaxy clusters and the distribution of matter in the universe. The study of black holes, from quantum scales to cosmic structures, continues to drive theoretical and observational advances. New facilities like the Event Horizon Telescope, gravitational wave observatories, and next-generation X-ray telescopes promise to further illuminate these mysterious objects that challenge our most fundamental physical theories while shaping the largest structures in the cosmos. The mysterious cosmic engines known as black holes exert a profound influence on our universe across an astonishing range of scales, from catalyzing individual atomic transmutations to orchestrating the evolution of entire galaxies. Mounting observational evidence continues to reveal their complex and sometimes surprising roles in cosmic history. The discovery of extremely early supermassive black holes has forced cosmologists to radically rethink formation timelines. Using state-of-the-art instruments like the Webb Space Telescope, astronomers have now identified dozens of quasars powered by black holes exceeding 10 billion solar masses that existed when the universe was less than 700 million years old, a mere 5% of its current age. The most striking example is the quasar J0313-1806, which harbors a black hole of 1.6 billion solar masses that had already formed just 670 million years after the Big Bang. This detection presents an acute challenge to conventional formation models, as it implies these cosmic titans somehow accumulated mass at rates that seem to defy the theoretical limits imposed by radiation pressure on infalling matter. Even if these objects grew continuously by accreting material at the maximum possible rate, the Eddington limit, they would need seed black holes of at least 10,000 solar masses to reach their observed sizes so quickly. This conundrum has led to renewed interest in primordial black holes as a potential solution. These hypothetical objects would have formed directly from density fluctuations in the superheated plasma of the very early universe, possibly during the inflationary epoch mere fractions of a second after the Big Bang. Their initial masses could span an enormous range, from microscopic black holes lighter than a grain of sand up to behemoths of thousands or even millions of solar masses. This diverse population could simultaneously explain several puzzling observations across different mass scales. The detection of unexpectedly massive black hole mergers by LIGO Virgo, involving objects of 30 to 60 solar masses, aligns well with predictions for primordial black hole merger rates. Meanwhile, microlensing surveys have detected signs of invisible compact objects with masses around that of Mars, precisely where some models predict a peak in the primordial black hole mass function. At the high mass end, primordial black holes could have provided the massive seeds needed to jumpstart supermassive black hole growth in the early universe. The environments near black holes create physical conditions that dwarf anything achievable in terrestrial laboratories. Within a few Schwarzschild radii of the event horizon, where spacetime itself becomes severely distorted, magnetic fields can exceed 10-15 Gauss, trillions of times stronger than Earth's magnetic field. Matter spiraling inward through accretion disks experiences temperatures over 10 million Kelvin and accelerations approaching 90% of light speed. These extreme conditions enable exotic nuclear processes, particularly the rapid neutron capture (R) process reactions necessary to forge the heaviest elements. The landmark multi-messenger detection of GW170817, a neutron star merger observed in both gravitational waves and electromagnetic radiation, provided spectacular confirmation of this mechanism. The accompanying kilonova explosion synthesized approximately 16,000 Earth masses of heavy elements in a matter of seconds, including substantial quantities of gold, platinum, and other precious metals that eventually find their way into planets like Earth. The influence of black holes extends far beyond their immediate vicinity through powerful relativistic jets and outflows. Accelerated by intense magnetic fields twisted into helical structures by the black hole's rotation, these jets can stretch for hundreds of thousands of light years, dwarfing their host galaxies. When these plasma streams, moving at velocities exceeding 1,000 kilometers per second, collide with interstellar gas clouds, they generate powerful shock waves that trigger cascading effects throughout the galaxy. The compressed gas forms new stars while simultaneously being seeded with heavy elements synthesized in the extreme conditions near the black hole. This process creates vast bubbles of hot, metal-enriched gas, as dramatically illustrated by systems like MS0735.6 plus 7421, where jets have carved out cavities 600,000 light-years across, large enough to fit 6 Milky Way galaxies end to end. The resulting distribution of elements follows complex patterns that we are only beginning to fully map and understand. Higher metallicity is typically found along historical jet paths and in galaxy clusters hosting particularly active supermassive black holes. Advanced computer simulations suggest that without the mixing and redistribution of elements by black hole jets, the chemical composition of galaxies would be far more segregated, with heavy elements remaining concentrated near their production sites. Instead, we observe a more uniform enrichment that points to efficient mixing mechanisms operating over billions of years. This cosmic recycling system demonstrates the intricate and somewhat paradoxical nature of black holes. While they are defined by their ability to trap matter and energy behind an event horizon from which nothing can escape, they also serve as engines driving some of the most energetic and transformative processes in the universe. Through successive generations of stellar death, black hole formation, and galactic-scale mixing, they have helped transform the primitive universe of hydrogen and helium into the chemically rich cosmos we inhabit today. The deep connections between black hole physics and galactic chemical evolution continue to be revealed through new theoretical insights and increasingly powerful observational techniques, from gravitational wave detectors to next-generation X-ray telescopes that will probe the hot plasma near black hole event horizons in unprecedented detail. The coming decades promise to revolutionize our understanding of black hole physics through an unprecedented convergence of new observational facilities, theoretical breakthroughs, and computational capabilities. The most transformative advance may be the Laser Interferometer Space Antenna, LISA, scheduled for launch in the mid-2030s. This space-based gravitational wave observatory will consist of 3 spacecraft arranged in a triangular formation with 2.5 million kilometer arms, connected by precision laser interferometry. By detecting ripples in spacetime from merging supermassive black holes across cosmic history, LISA will map out how these cosmic giants grew and evolved. LISA's exceptional sensitivity should enable detection of gravitational wave events out to a redshift of 20, when the universe was merely 180 million years old. This will test competing theories about the formation of the first black holes, including whether they arose from the direct collapse of massive primordial gas clouds or from the deaths of the first generation of population 3 stars. LISA could potentially observe hundreds of supermassive black hole mergers per year, with signal durations lasting months, allowing precision measurements of black hole masses, spins, and orbital parameters. This wealth of data will reveal how supermassive black holes at the centers of galaxies grew to their current sizes and shaped cosmic structure formation. On the quantum front, several experimental groups are developing ultra-sensitive quantum sensors that might achieve the precision needed to detect Hawking radiation from microscopic black holes, if they exist. Teams at leading quantum research centers are pursuing different technological approaches, including superconducting circuits cooled to millikelvin temperatures, trapped ions manipulated with precision lasers, and nanomechanical oscillators. While detecting Hawking radiation from astronomical black holes remains far beyond reach due to their extremely cold temperature, around 10 to the power of -7 Kelvin for a solar mass black hole, quantum black holes produced in particle accelerators or as remnants from the early universe could potentially produce observable signals. Theoretical physics is undergoing equally dramatic advances. The holographic principle, which suggests that the information content of any region of space can be encoded on its boundary surface, has evolved from a provocative conjecture to a mathematically precise framework through the ADS-CFT correspondence. This remarkable duality between gravitational physics in curved spacetime and quantum field theories without gravity continues to provide deep insights into the quantum nature of black holes. New ideas from quantum information theory, particularly quantum error correction, suggest that the apparent loss of information in black holes may be resolved by viewing spacetime itself as emergent from more fundamental quantum mechanical degrees of freedom. The development of fault-tolerant quantum computers could enable unprecedented numerical simulations of black hole physics. While current classical supercomputers struggle to simulate quantum systems with more than 100 qubits, quantum computers with thousands of logical qubits could potentially model the quantum behavior of matter near black hole event horizons. This could reveal how quantum effects modify classical general relativity in extreme conditions, particularly near the singularity where space-time curvature becomes infinite according to classical theory. Major quantum computing companies and research laboratories are pursuing different technological approaches, from superconducting circuits to trapped ions to topological qubits, in the race to achieve the required coherence times and gate fidelities. Observational capabilities are expanding dramatically across the electromagnetic spectrum. The Event Horizon Telescope collaboration is adding new radio telescopes to its global network and implementing wider bandwidth receivers, promising sharper images of black hole shadows and magnetized plasma flows. Next-generation X-ray observatories like Athena and Lynx will achieve unprecedented spatial and spectral resolution in studying the violent dynamics of heated matter spiraling into black holes, potentially revealing effects of strong gravity on atomic and nuclear processes. The James Webb Space Telescope's deep infrared observations are uncovering previously invisible supermassive black holes in the early universe, while proposed successors like Origins and Life promise even greater sensitivity to signs of black hole activity across cosmic time. These diverse approaches are converging on fundamental questions about the nature of space, time, and information. Do black holes permanently destroy information, or is it preserved in subtle quantum correlations? How does quantum mechanics resolve the classical singularity where general relativity breaks down? What happens to the quantum structure of space and time themselves in these extreme conditions? Black holes represent nature's most extreme laboratories, places where the known laws of physics collide and break down. They may hold the key to a deeper understanding of how gravity and quantum mechanics can be unified into a consistent theory of quantum gravity. The mysteries of black holes connect to the most profound questions in theoretical physics: the origin and fabric of space-time, the nature of information and entropy, and the fundamental building blocks of reality. As our theoretical frameworks mature, computational capabilities expand, and observational technologies advance, we are approaching a watershed moment in our quest to understand these cosmic enigmas. The insights gained could revolutionize not just our understanding of black holes, but our entire conception of the universe's fundamental nature. The next decade promises to be one of the most exciting periods in the history of black hole physics, as we push the boundaries of human knowledge into the most extreme regions of the cosmos. This new era of black hole science may finally resolve long-standing paradoxes and reveal deep connections between quantum mechanics, gravity, and information theory. The convergence of multiple experimental and theoretical approaches, combined with rapid technological advances, suggests we are on the verge of profound discoveries about the nature of space, time, and reality itself. As we peer ever deeper into these cosmic absorbers of light and matter, we may find they illuminate the path to a unified understanding of nature's deepest principles.